remember that laws describes what happens. So for example, if we have Boyle's law, Boyle's law is P1 times V1 is equal to P2 times V2. And this basically just describes that the pressure of a gas particle, like gas particles that exert on the container, it's going to be inversely proportional to the volume. So if I have a container, I have some gas particles in there, right? It's going to exert some sort of pressure. Now, if I decrease the volume of this container, the gas particles don't have to travel as far to hit the container. They can hit it more often. So it's going to increase the pressure. So if you decrease the volume, you increase the pressure. Now, Boyle's law describes what happens, but the kinetic molecular theories describe why do these things happen. And specifically, the kinetic molecular theory kind of gives a set of rules to how like a gas particle behaves ideally. So ideally, gas particles are in constant random motion. They travel in straight lines until they collide with another particle or the container wall. Gas particles, they occupy no volume. So essentially what that means is that the size of each gas particle is negligible compared to the space between them. So basically, compared to the volume of this container, these gas particles pretty much occupy no volume at all because the size is just so small. There are no attractive or repulsive forces between particles, aka gas particles don't have IMFs ideally. So gas particles, right, they do not attract each other. They do not attract each other. This does not happen. Number 5, average kinetic energy is proportional to temperature. All this stuff describes how gases behave ideally. But in reality, all gases in the world are known as real gases. All right, so they're not going to have this sort of ideal gas behavior. All right. Now, you can get pretty close to being an ideal gas, but a real gas can never be an ideal gas. Okay. Now, let's kind of debunk each one of these things. So, the only thing that can't be debunked is number 5, average kinetic energy is proportional to temperature. That's kind of the only thing that can't be debunked, but everything else can be debunked. Let's start off with number 4. Intermolecular forces do happen between particles, right? If you have two gas particles and, both of them are, let's say polar, let's say both of these are polar gas molecules, well, then they're going to attract each other, right? There can be some moment where these gas particles are attracted to each other. Okay? So the fact that this says that there are no attractive or repulsive forces between particles, that's wrong in the real world. Number 1, the gas particles travel in straight lines. Well, if these two gas particles attract each other, that can kind of offset the path of one of them. So gas particles, they don't have to travel in straight lines, right? Because intermolecular attractions can cause that path to be disrupted. Number 3, collisions are perfectly elastic. That just kind of means that when the gas particles bounce off the wall, they maintain all of that energy, right? And then they bounce off another wall, right? They don't lose any energy from bouncing off of the walls. And that's not right in a reality, because especially when maybe the temperature is a little bit colder, we'll talk more about that later. But essentially, like gas particles, once again, they could like slow down a little bit because of once again intermolecular forces. So the collisions might not be perfectly elastic. And finally, gas particles occupy no volume, which means, so this is basically saying that the volume that the gas occupies is equal to the volume of the container. So essentially, what this is kind of implying is that if we have a bunch of gas particles inside a container, this gas particle can move all around the container, right? The actual volume that the gas occupies is just equal to the volume of the container. We can just ignore it. But that's not true, right? Gas particles do occupy volume. And this becomes even more pronounced when you have a very small container. If you have a very small container, now the gas particles actually do take up a significant portion of that volume from ideal gas behavior. And under kind of 2 things, this is more pronounced. So real gases deviate the most from ideal gas behavior under low temperature and high pressure. So under a low temperature and a high pressure, this is when gas particles in our world kind of deviate the most from this kinetic molecular theory. Under low temperature, our gas particles are going to be moving slower, meaning that they have more chances of interacting with each other by intermolecular forces. And in addition, high pressure, right? Because high pressure, that's pretty much going to be the same thing as low volume, right? Because we saw how pressure and volume are inversely related. So if you have like a low volume container, it's going to have decently high pressure. And under a high pressure, well, the gas particles, they do take up a significant volume, right? So compared to the volume of the container is the ideal gas law. And what I want you to notice first is that things on the opposite side are directly proportional and things on the same side are inversely proportional. Ignore this R right now. This R is something known as the gas constant. Ignore that right now. But I just want you to focus on the pressure, the volume, the moles, which is symbolized by the N, right? How much gas you have, and the temperature. Notice how pressure and volume are on the same side. They're inversely related to each other. The temperature and the amount of moles is going to be inversely related to each other if we're keeping pressure constant. Let's do some practice problems with this. So a sample of oxygen gas occupies 5 liters at a pressure of 2 atm and a temperature of 25 degrees Celsius. And we want to find out how many moles of oxygen gas are present. So what I can do right now is I can kind of just plug everything into my ideal gas law. I know my pressure is 2 atms. Let's do up here 2 atms. My volume, that's going to be 5 liters. The amount of moles of gas I have, that's going to be, we don't know, right? So that's our unknown. This R right over here is a constant. This is equal to 0.0821 liters times atms divided by moles times kelvins. So atms, moles over kelvins. And finally, we have temperature. Now remember that for the ideal gas law, our temperature actually has to be in Kelvin. So if our temperature is in Celsius, what we can do is we just take the temperature in Celsius and add 273 to it. It's Kelvin. All right. So this is going to be multiplied by 300 degrees Kelvin. Right. And to isolate X, I just divide both sides by this, but I mean, this is just going to be calculator work at the end of the day. So our gas, so of our oxygen gas. Okay. If 6 liters of hydrogen gas at STP for this reaction reacts completely, what volume of ammonia gas is produced? And this is also at STP. So the ideal gas, it can be combined with stoichiometry. Remember that at STP, you have this following conversion. That's going to occupy 22.4 liters for your volume. So if we have 6 liters of our gas, that means that we can convert this into moles, right? If we have 6 liters of gas, this is 6.00. How many liters is this? I mean, how many moles of hydrogen gas do we have? 0.27, around 0.27 moles of H2, hydrogen gas. Now we say that 0.27 moles of hydrogen gas, we say that it reacts completely. So we're going to produce all the ammonia right over here. Now, what volume of ammonia gas is produced? First of all, we have to find out how many moles of ammonia gas have we produced, right? If all this hydrogen right over here reacts, it's going to create some amount of ammonia. How many moles of ammonia is it going to create? Well, there's a mole ratio right over here, right? We can say that for every 3 moles of H2 that we have, we're going to produce 2 moles of NH3. AKA, another way to think about this is if we have some amount of hydrogen gas, well, then the ratio between ammonia to hydrogen, that's going to be a 2 to 3 ratio. So we're going to get 2/3 the amount of ammonia than we started with for hydrogen gas, moles of ammonia. Now that we have moles of ammonia, remember that this is at STP, so we can convert this into liters, right? We can use the same conversion factor. So then, do not show your work like this, by the way, because I should do the work separately, like there or something, because these are not equal to each other, right? Only this is equal to this. But I make it seem like this whole thing is equal to that. Liters of ammonia. So this ammonia is going to occupy 4.03 liters. Okay. Notice how for problem number 1, it says that we are at STP. All right. So then we can use this conversion factor, right? This conversion factor can only be used at STP. However, STP conditions, by the way, and then it's going to be 1 atm for pressure. 1 atm. So that's going to be the conditions for STP. However, notice how for the second problem, we aren't at STP, so we cannot use this conversion factor. Instead, we have to use the ideal gas law. All right, we're given liters, which is volume. We're given the temperature, remember to convert that into Kelvin. We're given the pressure, and our ideal gas law, our ideal gas constant is always there, right? It's a constant, so it stays the same. So boom, we can just solve for moles if we're given 4 of these values, right? If we know 4 of these values, we can solve for the unknown. Also, the way I remember that I have to convert my temperature to Kelvin is that notice how for the bottom of the ideal gas constant, right? Notice how there's a Kelvin there. So if I have a Kelvin multiplied by a Kelvin on the numerator, right? Kelvin on the numerator multiplied by the Kelvin on the denominator, that's going to cancel out, right? So that's going to be good for my units. All right, it's always good to see which units cancel out to see if you're doing stuff correctly. So this is pressure, PV, so PV and RT. So this is my pressure multiplied by my volume. That's going to be equal to the amount of moles I have times this constant, liters, ATM, mole, Kelvin. And then this is going to be multiplied by the temperature in Kelvin. Our temperature is in degrees Celsius. So 35 plus 273 is equal to 307 degrees Kelvin of hydrogen gas. Now, in order to find out the volume for the ammonia gas, well, I know that I have this many moles of hydrogen, right? So then using the mole ratio, I get that, right, for every 3 hydrogen, for every 3 moles of hydrogen that I have, I'm going to produce 2 moles of ammonia. Once again, right, it's the same 2/3 ratio. Now, how do we convert from moles to liters? How do I convert from moles back into liters, right? Because we want to find out, volume, right? Volume is in liters in this case, right? So what volume of ammonia gas will be produced at the same temperature and pressure? Well, we can't use the conversion factor because this is at STP, but they're giving us that this will be produced at the same temperature and the same pressure. So we actually have to use the ideal gas law twice in this problem. Okay, so we know that. So in this case, right over here, if I write out the ideal gas law, PV equals nRT, it says that this is taking place at the same temperature and the same pressure. So we have both of these values. We also know the amount of moles of NH3 we have. So now we just have to solve for the volume, which we don't know. But if we know all 4 of these things, we can solve for the volume, right? So our pressure, remember, it's the same pressure that we had before. So it's going to be 0.950 ATMs multiplied by the volume. The volume, that's going to be, we don't know. It's going to be equal to the amount of moles we have times R, 0.0821. And remember, that's going to be liters. Sorry, not liters. Not just liters. Sorry. It's not just liters, it's liters, ATMs over moles times Kelvin. And then after that, our temperature in Kelvin. Remember that we started out with 307 degrees Kelvin. So that is what we're going to use. And boom, there's our equation. We can just solve for X by algebra of ammonia. And that's going to be my answer. All right. So if you're dealing with a problem like question 2, where you might have to convert from liters to moles, which requires the ideal gas law, then you use the mole ratio, and then you use the ideal gas law once again to convert back into liters. Now, we could have just solved this problem in actually just one step, believe it or not. All right, take a look at this ideal gas law. All right, this is saying that what volume of ammonia gas will be produced at the same temperature and pressure. So temperature and pressure are constant. So let's just cross them out, right, because they're constant. And we know the ideal gas constant, that's constant. Notice what we kind of have left. We have that the volume is going to be proportional, essentially, to the amount of moles. So if we increase the amount of moles that we have, we're going to increase the volume. Now, how can we use this to our advantage? Well, these are called mole ratios, right? These are something known as mole ratios, right? Because they're dealing with moles of stuff. But under constant temperature and pressure, you can also think about this as volume ratios. Volume ratios. All right. So another way to look at this equation under constant temperature and pressure is that 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of NH3. Right? It's the same concept as mole ratios, except because we know everything else is constant in our equation, the volume and the amount of moles got to be proportional to each other. So imagine if we started out with 7.50 liters of hydrogen gas. We can say that for every 3 liters of hydrogen gas that I have, I'm going to produce 2 liters of ammonia, right? 2 liters of ammonia, right? And then 7.5 7.5 times 2/3, that's going to be equal to, if we round to the correct number of sig digs, let's just assume we started out with 3, so let's just end with 3. This is going to be 5.00 liters of ammonia, right? Because the liters of hydrogen gas cancels out, you're just left with liters of ammonia as your unit. We got the same answer doing this. All right. The only difference is that, like, I rounded before, so this is like a little bit of error. But look, you can also use volume ratios as well to help you solve this. Pretty cool. So for the ideal gas formula, right, it's PV equals nRT. Imagine if we divided both sides by RT. We're going to get PV over RT is equal to N. Now, let's say that if we only had 1 mole of gas, aka N is equal to 1. So that means our PV over RT is equal to 1. All right. Now, remember that this is the ideal gas law, right? It's when gases behave. It only kind of works when kind of gases behave ideally, right? We're under the assumption that gases behave ideally. But what happens if they don't? Let's take a look at a graph of this. So on the x-axis, we have basically the external pressure. So essentially, the external pressure, right? We can think about it like that. And then on our y-axis, we have this PV over RT ratio, assuming that N is equal to 1, the amount of moles we have is equal to 1. Now, ideally, you would expect the pressure volume over the RT ratio to be equal to 1 if it was ideal gas, right? Because for this formula right over here, right, notice how we converted it so that when N is equal to 1, our ratio is equal to 1. Under actual conditions, so when real gases actually behave, they don't follow this 1 ratio. Instead, their curves would look something like this. So you would have, as pressure increases, maybe you have like a little bit of a dip, and then after that, the pressure would go up. Or I mean, the PV over RT ratio would go up as the pressure goes up. Now, what I'm going to tell y'all is that what's responsible for this little dip below 1 is actually going to be intermolecular forces. So what's responsible for these graphs dipping below 1 is intermolecular forces. Because if you kind of think about it, right, if you have a container, let's say it's at a certain like atmospheric pressure or something like that. Well, due to intermolecular forces, when a particle hits a wall, they're going to be attracted to other particles, right? And therefore, they're going to hit the walls with less force. Therefore, the pressure of this equation, I mean, this thing right over here, this expression, would actually be lower than what's expected, right? Your pressure would be lower than what's ideal. And therefore, if you decrease the numerator, well, then your graph is going to dip below 1, right? So because of intermolecular forces, our pressure is going to be lower than what's ideal. Therefore, this graph is going to dip below 1. Now, if we take a look at this higher part over here, where our PV over RT ratio is greater than 1, well, this can be explained by real gases deviating from the ideal gas, in the sense that real gases do take up a volume in the container. So remember back from the ideal gas law that when you're doing a PV equals nRT, this volume right over here represents the volume of the container. However, the problem with using the volume of the container as your V value is because gas particles do take up a volume in the container, right? Right? Because if we have all of these gas particles right over here, right, the actual volume that the gas particles have in order to move would be the volume of the container. Minus the volume of the particles, right? Right, so the volume of this, the actual volume that the gas particles have, like the actual space that the gas particles have to move, is going to be equal to the volume of this whole container minus the volume of the gas particles, right? Because the gas particles do take up a volume. And this is even more pronounced with higher pressure, because, right, notice how as pressure increases, well, the container is going to get smaller and smaller, right? So if we have an even smaller container right over here, right, the actual volume of this container is going to be less than the volume of the container, right? The actual volume of which the gas particles can move around is going to be less than the volume of the container. However, we still continue to use the bigger value, which is why the PV over RT ratio is going to skyrocket up. All right, so this is why the PV over RT ratio gets bigger than 1. It's because the actual volume for the formula is not used, and the volume of the container for this formula is used. But the volume of the container is bigger than the actual volume the gas particles sort of have to move around. So because we're using the bigger value, well, you're essentially increasing the amount of volume, right? The actual volume. So that increases the numerator, which makes this line go up past 1. Now notice how we have two different temperatures right over here. I have CO2. Both these represent basically the PV over RT ratio for CO2. However, one is colder, one is a sample of CO2 that is colder, and one is a sample of CO2 that is hotter. And what I just want you to notice is that the colder sample of CO2 has a lower dip. And this sort of makes sense because remember that real gases deviate more from how ideal gases behave under high pressure and low temperature. So look, the high pressure thing you could clearly see on the graph, right? As pressure increases, we deviate more from this PV over RT ratio of 1. And notice how at low temperature, we deviate even more because guess what? Remember how I said when gas particles, they travel slower, they're going to have more chances to interact with each other by intermolecular forces, right? Because if the temperature was very hot, the particles would just be zooming past each other. They would not have time, or, they would have less time to, sort of attract each other. But because the particles are slower, now they have more time in order to interact with each other, and the chances of intermolecular forces playing a role in the pressure would increase. So I just want you guys to notice that the colder samples are going to deviate more from the sort of ideal gas law than the hotter samples. And, this pretty much just sums it up.